Welcome to another robotics seminar. Matt is losing his voice, so he brought an interpreter. He brought. You want me to say in your? Okay, fine. I brought an interpreter. Yeah. Today we have a wonderful speaker. But first I'd like to say that all MIT alumni are weenies. Yu Wang was my first PhD student.
And he has won many impressive awards.
And he has won many impressive awards.
And he spent time in the University of Maryland.
And he spent time in the University of Maryland, Chinese University of Hong Kong,
and National University of Singapore.
And now the National University of Singapore.
And he is well known in all places where excellent design work is done.
And he is well known in all places where excellent design work is done.
For his level set methods.
For his level set methods and many other things. So join me in welcoming Michael.
Thank you very much. Thank you so much, Matt, for this kind invitation. Back to CMU, I told Matt, all you have to do to introduce me is to say, you was my first PhD student. In our lab back then, there was a writing on the whiteboard. Randy Brose did this. He wrote that you was here. Right. So I brought you right in the middle over here. And Michael is just super vicious. It's not relevant, not that important. So I'm thrilled to be back to CMU, where I graduated 25 years ago. And I haven't been on campus for more than 22 years now, I think. And a tremendous amount of changes have happened, all for positive, and extremely exciting. The Robotics Institute has grown to such an exciting level, and I'm really happy to be here to share with you very briefly, hopefully in about 40 minutes or so, some of my research work and also some of my thinking for working in robotics again. Although I was trained as a robotist, but I have been doing a couple of different things over the time. And hopefully I will be able to do more robotics from now on, because I just moved to National University of Singapore. It happened that Singapore is going through a major transition. Its economy has reached the point where it has surpassed Hong Kong with a GDP per capita about 55,000 US dollars. For USA, for your information, it's about 66,000 US dollars. And Singapore now is facing a big problem with labor, with 5.5 million people living in a small island on Singapore. 2 million of them are holding a work visa. So they are not Singaporean or Singapore people. And with the rapid labor import, there are now big social issues. Education, housing has become a major problem. So government now is hoping that robotic technology would alleviate some of the labor problems and reduce the labor demand, also increase productivity. Now, National University of Singapore, let me just give you a very brief introduction about it. It's a fairly large institute, It has 27,000 undergraduate and a little bit over 10,000 graduate students. And Faculty of Engineering is one of the largest. We have full-time faculty members of over 300, and our undergraduate and graduate altogether a little bit under a third of the whole total student population. So we have a large number of students, very large classes, typically 300, 400 students in one lecture hall. And engineering is a key factor in its economy. It accounts for 25% of GDP. So it's not like Hong Kong, where I used to be for 15 years. And at the Chinese University of Hong Kong, the size is about 1/3 of National University of Singapore. And the GDP percentage of industry is 0.02%. The entire industry has about 20,000 people employed in whole Hong Kong. So engineering pretty much irrelevant in Hong Kong. Although that universities there were pretty good, but the scale of research is really not much at all. So at NUS, our Faculty of Engineering has an annual research expenditure around 75 million US dollars. And in Chinese University of Hong Kong, whole university, the annual research expenditure is 25 million US dollars. Okay. You are the director of Robotics Institute, and you know the numbers, right? $25 million is a cupcake for Robotics Institute. So you understand the scale of the research. It's really, in a very small country like Hong Kong or Singapore, it does take quite a bit of effort from the government as well as from economy to develop strong research programs. So that's the nutshell about Hong Kong and Singapore. So today I'm going to give you a very short description about some of the new robotic technology development area, which I think is important. And I will give you some of my thinking or my background, where I have done some work in compliant mechanisms, and I will relate that to where I think that some of the new development in hyperelastic robots might be related to compliant mechanisms. As a mechanical engineering student, that's where I got my PhD from mechanical engineering. When I was a student in Carnegie Mellon learning robotics, this is how we start our learning. We look at the robot in terms of the kinematics first, then we examine the structure and dynamics, then we close the loop, put the feedback control into it, and then you would have an articulated machine, which we call the robot. Okay? And in this framework, the design and the development of a robot is very clear. You start with the Kinematics Theory, which was given or developed in 1875 by Frank Rolex, that assume that your key elements of your machine are rigid bodies, and they are connected through kinematic pairs, and therefore you will be able to have your degree of freedom, you will be able to generate motion. And then of course, then you need the structure integrity, so you put materials into your structure, and then you would have your dynamics, and then you construct your feedback control. So essentially through the forward kinematics, you decide what kind of a body structure you need. So either a serial connection or parallel connection. So that's the major part of the kinematics. And then through the inverse kinematics as well as the dynamics, and you build your control law or control policy. So with that framework, we are very successful in developing machines or in building robots, in particular the industrial robots, where our performance goals are really the precision, the speed, as well as the payload. Right? And we concerned a great deal about the structure integrity in terms of the stress strains in the structure as well as the dynamics. So we are tremendously successful in developing those industrial robots and being applied in a variety of industries, in particular in automotive engineering. That essentially what brought the robotic technology to an industrial level. However, if you look at this type of robots, when you wanted to make use of them to interact with human beings or being part of assistive devices that could be connected to human beings, you will find this type of technology is very awkward, very difficult to make use of. I'm sure you have seen some of the pictures as well before. So particularly the whole framework of robotics design is really look at these three key attributes. You want to have end effector, you want end effector to have fairly good speed at a given precision, carry very reasonable load, could be as high as 100 kilograms. And essentially over there is that you care about the kinematics and dynamics as well as control. There are really very little concerns about the interaction with the environment. Essentially, you let your robot run where you are very much open loop environment, open loop fashion. When it runs into the environment, somebody is going to get hurt. Okay, so essentially, for industrial robots, you have to put a cage around it so that it will not be really much involved with interaction with human beings. Now, if we want to get the robots to interact with us or to help us, when we get into the interaction part, then the key attributes could be totally changed. We are looking at interaction, we are looking at sensing, we are also looking at the communications. So in this new domain of robotic applications, the attributes are very different. Okay? The performance requirements are very different, and therefore the platform or the framework of the technology may have to be changed. We will have tremendous difficulties directly apply the industrial robots to do the human interaction activities. So one of the major idea of getting robots to be compliant enough to interact with environment, interact with human beings, is put the variable stiffness into our control loop. So you probably have seen some of the videos where the robot might be able to even punch a face of a human being without creating a severe damage. And that technology is developed by DLR lab in Germany, and there are only 1 or 2 brave souls on the earth willing to take that test, right? And he's, of course, very famous now. And his technology essentially between your actuation unit and the end effector, that you build a artificial stiffness. You build element in that, either physically or through your control loop. To be able to do that actively, you essentially need multiple sensors as well as very high bandwidth in your control loop to be able to regulate that. So this technology now is transferred into a commercial product of a KUKA robot. It's essentially 6-degree freedom robot, but it has 26 degrees of freedom internally altogether. There are 52 motors inside this 6-degree framed robot and 112 sensors. Okay? And that tells you the complexity, also tells you the demand on your control system. You really have to build highly elaborative control systems, control loops, relying on your sensing as well as the bandwidth of your system to be able to achieve that kind of compliant behavior. The cost is fairly high, easily over 100,000 euros. And in fact, it's only limited number of these robots are now on sale. In Asia, KUKA is not planning to open the market at least for 3 years. However, US, through some personal connection, got one of these under the first batch of the funding, government funding for robotics of 20 million Singapore dollars. So we have to figure out how to make use of it, even though it's very elaborate, very sophisticated. So there is another line of thought, that is, look at human beings and see why not to make robot compatible with the environment or compatible with human beings in physical sense, in passive sense. So if you look around, some of the stiffness properties of some of our living tissues or living structures, you will find that stiffness of the typical human tissue is around 1 megapascal. So our cartilage, our muscles all have a stiffness around that number, okay? Which is extremely low compared to metal, for example, aluminum, which is 10 times of 1 gigapascal. So metals and all that is over here. Okay? So this is what we normally consider as rigid bodies in our kinematic structure of the robots. So if we make our robots out of the materials with similar stiffness property, so essentially physically you would have what we call compliance matching. Then you do see the material properties of your robot and the environment, all the creatures, animals that are interacting with your robot would be in the same order of magnitude in terms of at least the stiffness property. So this is where the idea that people would think that should we build a robot or build any machines that when we interact with the more or less the same stiffness, that we might be able to alleviate all these interaction issues, or at least in terms of damages. So if you look at a little bit more closely in terms of technologies, there are a number of critical elements are already in places. So there are soft materials which you can use to create actuators. There are also soft materials we might be able to use as sensors. There are also soft electronics today are being developed. And by putting some of these elements together, we might be able to create robots that have those three attributes: being able to interact with you, be able to sense, of course, being able to communicate. So that's the fairly rough idea of developing soft robots. Okay, it's a very vague, very general. It's not very specific. There are a lot of issues and questions. Of course, number one issue would be actuators and the sensors, right? And soft actuators are very different from electrical motors. And then if you are able to develop these devices, and what would be the machine that you have to build. So from that point of view, there are some latest development and which have got a little bit of attention in robotics community. So this is in particular, some of you probably have seen this. It's out of the Whiteside's group in Harvard School. He built one or two of these devices out of silicon rubber, actuated through pneumatic pressure. So we'll be able to move, in this case, as a gripper, in the other case as a locomotive robot. And when this came out, quite a lot of people get very excited. They said, oh, this is an age of soft robots. And when I look at this and see, well, these are done by chemists. Okay? And they happened to know certain processes and then able to put a couple of pieces together. They call these robots. Okay? And from my background, from how I was trained as graduate student in Carnegie Mellon, and if you want to call these robots, you're going to have to be able to see much, much more about it, right? So that's what I'm trying to say. If this is a robot, what are you going to have to do? So if this is a robot, then what you have is a soft body. You may have skeleton structure into it. You might build skeleton structure into it, just like the traditional industrial robots. You could have rigid links with joints, and you can put motors over there. And of course, you could have joint actuators, and you can also embed soft actuators, like pneumatic actuators or pneumatic bubbles inside your soft body. And then you might want to embed sensors. In addition to the joint sensors, you might also embed the strain sensors and compression sensors and stretch sensors into your soft body. And altogether, you might be able to say that you have a soft robot. But still, you need to be able to say what are the functions of this robot. Can the robot do locomotion, or can the robot do manipulation? So there is that side which is not clear in the first picture I showed you. Okay. And if you look from that perspective, and this is very different from what I learned in the design of industrial robots. So you're going to have asking questions about what is the kinematics in this robot, and what is the dynamics, and what would be the right control. Okay? And in the end, very importantly, you have to be able to answer what the robot can do. Can it grasp or can it manipulate? What kind of things, task can it accomplish? So from that perspective, then I'm now started to think about what would be the framework in terms of a design, analysis, as well as control of such a robot. Of course, and you have to be able to build such a robot physically to fulfill that. So to me then, from a mechanical engineering point of view, from mechanics point of view, this robot is really a structure. If you simply ignore the skeleton system inside, you really have nothing but a piece of material. Essentially is a structure, okay, that happen to be able to deform with large deformation if that is what you want. And it does not really tell you much about the functions of the robot, okay? What kind of a task you're able to accomplish. So you need to be able to analyze that, or need to be able to model that. So key element for me, the key issue for me is to be able to design, model such a system, and then come up approaches for design, for analysis, as well as for control. So I'm stepping back to the very fundamental level, looking at this as a system of a structure, and trying to then make the structure to be able to behave as a machine to give us the desired function we want. So along that line then, essentially, the manipulations you are able to achieve is the interaction of a part of your structure with object in the world. The locomotion would also belong to the interaction of a part of your structure with ground, for example. And it's just that in the rigid body robot, we call these interaction parts feet, okay? And these interaction parts hands or fingers. Here, of course, you can deliberately designate part of your elastic body as fingers and as the feet, but essentially now is a continuum structure that happens to be able to actuated and controlled to accomplish certain tasks. So when I look at all of that, and then I realize this kind of perception, this kind of thinking actually is being discussed and being simulated in computer graphics. So here at Carnegie Mellon, Nancy has done, or her group has done a wonderful work where they have modeled a Michelin man as a elastoskeletal system. So it's a rubber-coated person with a skeleton system inside, and she has developed controllers to be able to make the man dance on the floor, as well as some other similar structures. And at Georgia Tech, Karen Liu's group also have done some work in terms of simulation, where she would treat it a machine, she doesn't call it a robot necessarily, inside that piece of a jelly-looking structure. She assumed there are some tendons. These tendons could be contracted if you command it, and under the contraction of the tendons, and this jelly piece would be able to dance and move forward, as well as some other structures would be able to do some other work. So in fact, the concept of soft robot or hyper-elastic robot is already there, although this is just virtual. The actuations, the sensings are pretty much assumed to be there or assumed to be functional, and nothing has to be built. Okay? So for me, that I would think it's a very good idea, a great idea. If we are able to build them, more importantly, if we know how to design them. Why should it look like this? Why should it look like Michelin Man, right? What would be the right body structure, just like the articulated kinematic chain we use for rigid body robots. So these are the issues that I think that important, I think need to be examined and looked very carefully, and then perhaps then we would have a framework to allow us to build ground up of elastic or hyper-elastic robots. Of course, we need technology elements of actuators and the sensors, and those definitely need to be put in place. So if you look at that, then what we are looking at really is a system where we need to worry about design, modeling, and control. So design at the very front, where you need to worry about the body type, skeleton articulation, what kind of sensors, actuators you need to build into your system. Then, of course, you need to relate to the task that you want to accomplish. You build your robot, design your robot for a particular task you would need the robot to do. It might be locomotion, it might be manipulation, it might be simply just the interaction, shaking hand with a human being. And once you have that, then you need to build your controller that will deal with the hyper-elastic material properties as well as dynamics. And so essentially, this is a highly distributed system because a continuous system, and you need to have a reasonably designed controllers to be able to handle the complexity of the dynamic system. But part of that is already being discussed by the computer graphics community, interestingly. So what I'm going to show you is just to say that most of these fundamental analysis tools are already in place. The fundamental mechanics are already in place. So in terms of the hyper-elastic body, the mechanics is well understood. So we are so much getting used to the kinematics of a robot, but in terms of the elastic deformation of any type of hyper-elastic material, you can easily build a model that allows you to analyze it. I will not get into the details. So this is related to continuum mechanics, nonlinear continuum mechanics of a large deformation of a piece of material. So in fact, in the medical simulation area, simulation of the tissues, body parts, as well as the surgical operations on body parts, as well as some other areas such as articulated characters and balloons. So these are simulation and analysis done by Disney Research in Zurich. So fundamental work already done. We can easily handle, easily model any type of a structure that can go large elastic deformation. On the actuation side, pneumatic actuation of soft material is fairly common, fairly general. It's just that it's not electric, meaning that you would have a relatively large supply system, and also pneumatic actuation is a mass transport. So it's not very efficient, it's not very high power, it's very slow. So to be able to come up actuations that are relatively more practical for robotic applications, we really prefer using electrical control. So the only type of technology that really is now available even though it's still in the preliminary stage, is the dielectric elastomer. So this is typically just natural rubber or kind of a silicon material where when you apply high electrical charge and you force the material to deform. Essentially, the charge would like pressure and cause the material to expand. And you may be able to expand a dielectric elastomer up to 300%. So you can create fairly large deformation. And over the last 10 years or so, a group researchers in particular saw at Harvard has done the scientific analysis on the behavior of a dielectric elastomer. So essentially, today we knew very well about the behavior of this type of materials, and you can build actuators, although they are not that very easy to be used. I'll tell you what some of the practical limitations, and there are a great deal of models and being fully developed, and we don't need to get into the details. So in terms of a control, the framework is also well developed. Essentially, it will be optimization-based system where you would have your objectives, okay, and you have to deal with the dynamics, full dynamics of your hyperelastic systems. And in particular, you need to also deal with the frictional contact where your robot may interact with objects or with your environment. So the frictional contact is part of the classical problems in robotics grasping. Normally, we'd apply the complementarity principle, and that would allow us to fit that into a control loop. And of course, then you need to have a lower level controls, such as momentum control, gate control, and balance control if you are looking at a hyperelastic robot. So essentially, this is what Nancy and some others have done in computer graphics. They have come up with relatively robust, fairly efficient control laws based on optimization controls, and to be able to give you that kind of simulated performance. So to me, that all these elements are more or less in places. Okay? And the only question that the fundamentally have not answered to me is the design. So now, what is the kinematics of this robot? Dynamics, I can write down the dynamic equations. So how do you describe motion behavior of a piece elastic material? Okay. If you're a mechanical engineering student, if you have taken some of the mechanics classes, in mechanics classes, they never talk about motion. Structure is not supposed to have motion. Structure's mobility is zero. That's what we learned. Now, you want to have motion out of a structure. So essentially, you're taking strain or displacement or large displacement at some part of your structure, and you want that displacement to behave, to function the way you want it from the robotics point of view. So that part is what I began to focus on, and there are a lot of words here. I will not get details into this. So essentially what I'm trying to say is that to compare with the classical framework of kinematic or motion analysis of a robot, there really not much has been developed for a continuum structure or hyperelastic robot yet. So we need to come up a system, come up a approach to answer that question. That's what I started my work. So in fact, the work started not in a general robotic sense. My work was more related to mechanisms. So similar questions were asked in mechanisms where people have suggested to not use rigid links, but rather use elastic members or elastic structure to come up a mechanism that's very much similar to a rigid body mechanism. So it's called compliant mechanism. So idea there is really very similar to the issues that I had just talked about, although it's a little bit simpler. There we are looking at an elastic structure, and some part of the elastic structure we are giving actuation, some part of the other part of the elastic structure, we have large displacement, which would mimic a motion of a rigid mechanism. So essentially, again, it's the structure where you have certain input at some point, and you want at certain other points, you want to have certain displacement behavior. So that's what is what is required. So along that line, there are a number of different approaches to deal with this. I've just mentioned that compliant mechanism has been around for about 20-some years. It has found very good applications in medical instruments as well as in morphing ring structures. Today, there's a great deal of development of morphing wings in aerospace, and quite a lot of ideas are based on the compliant mechanisms, where you want to have a piece of a structure that you can change the shape, but they are rigid enough to resist the thermal, the aerodynamics. So that's the one of the area of the applications, and a compliant mechanism being used quite extensively. So from that perspective, it's really much the similar issue that I asked myself, where if you look at the classical mechanism design, it's all based on Frank Rulick's theory of kinematics, where you have rigid bodies, you have a kinematic joint, and now you are going to fully replace rigid body joints with just continuous body. And how do you develop your mechanism? So the framework now is very much based on the idea of optimization. Okay? So I would have an objective function, I flashed right up there already, where I define certain displacement relationships. For example, the displacement at one point, output displacement, and versus displacement at the input or force. I want that to be very large, or as large as possible, but my system is confined into the elastic system, elastic structure. So essentially, I will need to work with the structural mechanics. I cannot ignore that at all. That's all I have, but I want to have this structure to have certain behavior in terms of a function, which I need to maximize or minimize. So I cast everything as a structural design problem. So design robot or design compliant mechanism now becomes a design of a structure. It's structure optimization. Okay? So I will get to that very quickly. I will show you some results. Then I will come back to say whether or not this might lead us to more generalization into design of a hyperelastic robot. There will be a great deal of details which I will not be able to get into. Structure optimization by itself is a big discipline. It has quite a lot of people getting involved. Majority of them are from aerospace, and nowadays mechanical engineering people are also getting involved because of the potential applications. So one of the approach that I have taken is to look at the structure and define the structure by a level set function, such that I'll be able to describe the boundary of the structure and also be able to change the boundary of the structure in any way I want it. In particular, I'll be able to change the topology of the structure. So this way, would allow me to, through the optimization, to come up the best topology of the structure as well as the shape of the structure. So I use the level set technique, which I will be not able to get into the details. There are a lot of equations of that. So essentially, you start with the structure, you're going to change the boundary of the structure. But as you change the boundary of a structure, you also be able to change the topology. In other words, I'll be able to create more holes, able to merge holes, I'll able to get the shape change in a very dramatic fashion. Okay, so I will be able to come up a optimization system. Typically, it's an iterative process. We'll start from an initial design and going through the iterations. In the end, I would come up a final structure which give me the required performance. In particular, that relationship between the input and output displacement. I will ignore all the details. It's going to take too much of that. So just to show you a couple of examples. These are the compliant mechanisms. So this is what we call a micro gripper. So the concept is very simple. I want to design gripper that would have a range of motion in micrometers, and which might be able to grab a biological cell, so on and so forth. And the gripper needs to be small, so I'm going to just build the gripper with one piece of material as the structure. But so it behaves like mechanism of gripper, but essentially it's a structure. So the design here, I took top half of it. It looks very strange. So it's a 2D design. Top half of it, I started with a lot of holes. And then gradually it will remove the materials and combine all the holes and eventually give me a structure that allows me to have the close and opening of that jaw. On the right hand side, that's the level set function, which for now you can just simply ignore. Okay? So essentially what I'm trying to say is that level set function, if you look at it, it is nothing but a one continuous function. And the structure is zero set of that function. That's why you see a lot of holes, or different sizes of holes, and you also see the change of the holes. Okay? Because you operate in here, you optimize in here, your structure is embedded in there. So that's the advantage of that. So that's a very simple result. That's a micro gripper. So when you pull one of the end, the two jaws would close, open, and really not that fancy. But it's a compliant mechanism. There are no revolute joints, no sliding joints. So essentially you don't have the issues with backlash, with friction. And this could be easily fabricated, in particular in today's wide applications of 3D printing. And you would be able to fabricate this kind of devices very easily. And you can, of course, generalize it into three-dimensional. So here's one of my former PhD students who came to US, and he did the three-dimensional of the same problem. And you would end up with a 3D version of a simple gripper as well. And the design process is purely computational. It's all based on optimization functions, which define the behavior you wanted, and the constraints, which essentially says that is a continuous structure. And the level set model, which allows you to change the geometry very much arbitrarily, so that you would eventually converge to whatever the best the design there is. Okay? And so that's essentially what we've been doing. And we also look at the possibilities where you might want to make use of multiple materials. Instead of just a single type of material. So over here you have a green and blue. Blue is a stronger material, green is a softer material. So you may ask questions, well, what if I use multiple materials? What kind of a gripper I might end up with? So you see over here, this is where you will have large bending or large rotation displacement, and the most soft materials put in place, but all other places is more like what you would have for single material. And so this would be a similar set, one material versus the two materials, and essentially there's really not much difference as far as simple compliant mechanisms concerned. So using multiple materials, using softer materials versus harder materials, in this case, only difference is where you have a large bending, then the soft material tends to go there. Okay? And we can also have multiple functions. So over here, it's just a simple example where you have a vibration harvester undergoing a compression elongation. What you want to do is to recycle that vibration motion and generate the electricity. So therefore, in your structure, you would have some piezo materials under compression would be able to generate electricity. So the question is, what would be the right structure where you have the structural part as well as the piezoelectric part? The piezoelectric material is described in terms of in the red color. So you need to have a right balance. If you have too much of the structural material, you won't get much of the deformation. Okay? But if you have too little of a piezoelectric material, then you will not be able to generate electricity. So piezoelectric material is fairly hard. So when you mix these two, what would be the best balance such that you will have a best efficiency? So what essentially we are trying to show here is that you can have materials, different materials with totally different functions, and they could be mixed into this optimization framework, and in the end, the best design would be given to you. So the multiple functions could be generated. So it's just an example to show you that. Okay. So that's about all there is in terms of a compliant mechanism. That's what we have done. We have done compliant mechanisms for in 3D, in 2D. We have another program now. We are building materials that have negative Poisson's ratio for morphing applications. So that it has some good properties. So we'll not get into that. And then we look at that and say, how do we generalize this into our hyperelastic robots? And it turns out that it's still very, very difficult. This is all we have done. We have not been able to move any further. But in terms of materials, in terms of building this type of soft robot, it's actually not hard at all. Okay? And if you get get some silicon rubber, and you can easily mold them into a gripper like what Whiteside have done. And you can build pneumatic chambers, and you can pop air into it. You can see the grasping motions. And for very light object, a cup and piece of paper, and these kind of so-called grippers certainly can do some work. But their load carrying capabilities is very, very low. Okay. If you put 20-gram weight on it, it will not be able to hold it. So obviously, very soft materials will give you very soft behavior. You will not be able to make use of that much. You can also keep track of the deformation, compare the deformation with our hyperelastic model, with all the complicated equations I showed you earlier. And the models are very accurate. It's not up to micrometers, but up to tenths of millimeters at least. So in terms of the precision, here at most you can achieve around 1/10 of a millimeter. So the precision will not be that high, and there's actually no consideration of dielectric elastomer actuator into there yet. Okay? For the dielectric elastomer actuator, the fundamental physics is well understood, and there are a number of actuators being built demonstrating that these materials under high voltage, typically a couple of thousand volts, and they are able to deform with large strains, a couple of 100%. So you might think that might be a very useful material. But these materials' behavior mechanically very much like elastic material. When you apply stresses, it will basically give you strain and elongate very much. Electronically or electrically, the behavior is a bit more complicated. There are a number of different failure modes, rupture, electro-mechanical instability. So essentially you will get curved like this. But the worst part from application point of view is this problem, where you need a pretension on the material. Then you apply voltage, and then they will expand, acting more like actuator. But without any pretension, if you start from here without any pretension, if you apply voltage, nothing would happen. Okay, so the electrical charge would simply become heat dissipating on your material. You can easily burn it. Actually, we have see fire on the dielectric elastomer. So pretension is a very big problem. So how do you put pretension on a piece of elastic member where the structure of it, supporting it, is elastic as well? So okay, you can easily put the elastic member under tension onto a rigid body, but on another elastic body, it will create compression on the supporting structure as well. So everything would crumble together. So having this is really a nightmare, and that's why the dielectric elastomer actuators have not been very well developed and used. So one of my students now is working on a bubble actuator. Very simple idea. So the pre-tension would come from air pressure initially inside a balloon made out of a dielectric elastomer. Okay? So as you then apply charges on the surface of the balloon, it will be able to expand, but the internal pressure would drop. So your performance would gradually deteriorate. So you would have only limited small window where the actuator might be able to operate. So that's where this design needs to be worked out. But the nice thing about it is that if I can build the balloon actuators, I can really embed into a soft body as actuator, or I could distribute this in multiple actuators inside the body. And furthermore, I can build a network of these actuators. So two balloons could be connected through an air channel. So they would actuate differently, but through internal air channel, you will get more complex behavior. So it would give you more authorities over your control. So building this now is still a challenge, but analysis, I will just flash this at you very quickly. The mechanical part, electrical part, throw them all together, and we will be able to stretch it under these parameters about 30 to 50%. I don't have a chart over here. Essentially, what it says is that initially you are at some pressure at some point, and you are able to operate in certain range until you hit one of the limit lines, either electrical, mechanical breakdown, or rupture, or you essentially lost the pressure, all of that. So you have a limited window, but by carefully twinkling all the parameters, there will be a right size of a balloon with the right thickness where you will be able to expand about 30 to 40%. So this is where we are still working on. But how to build that, we're not sure yet. The biggest problem now we are facing actually is electrodes. Okay? So you have the hyperelastic material, the dielectric elastomer, and you need electrode on one side, electrode on the other side. These electrodes need to be flexible as well. And there are very few choices of flexible electrodes. So development of flexible electrodes now are actually much more critical, at least in our application. So in one of the pictures I showed you, you see some black color on the surface. These are carbon grease. They're just the dark carbons made into the grease. You simply rub them on the surface. The conductivity of it is not very good, and over about half day, they became quite dry, and they would lose the conductivity and the stretchability. So that's all I actually have. So that's essentially what my focus for the research on soft robots or hyperelastic robots. At least in my mind, I think there are major issues, in particular from the design point of view. What would be the right body? How do you model it? Okay. How do you create the motion you want? And when you get to the control part, it's getting far more complex. The interaction of your robot with the ground and also with your object. So in terms of manipulation, that interaction is very crucial. In terms of locomotion, then the gaze control, frictional behavior, that all need to be fully considered. So all of that is up in the air, and hopefully more people are getting interested in this area. So I've just leave you at this point. I have more questions than answers, but that's all I have done, right? So in my mind, that soft robots or hyperelastic robotics, there are still quite a lot of room to grow. There are great potential, and the key bottleneck today are the materials themselves, as well as actuators and the sensors. So the devices are not there yet, and design methodologies are not there yet. And more importantly, a lot of people ask me the question about applications. what are you going to do with these robots? Okay? For now, all I can think of are the picture of Nancy's simulation, this Michelin man, and this is jelly jumping simulation. So I told my students, if we are able to build these robots, if we're able to drive them electrically, dancing Michelin man would be impressive, I would think, right? So we will see what other applications we might come up. So it's still in a very infant stage. So that's pretty much all I have. I have a roadmap, how to get there. And part of the issues are the integration of electronics with the materials. So we have a number of technologies today, especially 3D printing. So I think 3D printing will play a role in the fabrication of these robot devices. And with that, I would just say that fairly preliminary. There are fundamental issues that need to be looked at that. And I also need to mention that there is a group of researchers pretty much in Europe and in Zurich. And they are much more interested in intelligence embodiment. Okay. So Rolf Pfeiffer, right? Pfeiffer's group and some others, and they're sort of trying to connect with software robotics community and answer some of their questions. Okay. With that, I think I will just stop here. We'll just mention some of my students and some of the collaborators. And over the years, when I've been in Hong Kong, we have some small grants. Typically in Hong Kong, we as a researcher or professor, our national equivalent National Science Foundation allows us to write one proposal a year. I cannot submit the two. Okay, only one proposal a year. The typical grant size is about $100,000 US altogether for 3 years. So you can only support one graduate student on each one of the grant. But luckily, I had some grants from China. There's a lot of money there. And if you are able to tap into that resources, then they have also a lot of students. But Hong Kong and China are one country, two systems. Money do not allow to cross. So I have to go to China to supervise students to do the project. Okay. And now at Singapore, and we heard the government is going to put quite a bit of money into robotics. Hopefully then I'll be able to tap into that, some of that, and to do some work on this basic research. That's all I have, Matt. That's all. Thank you.
Answer some questions.
You need me to translate for you? Questions?
I have a question. So Vincent Hayward was here.
What's the Hayward?
He was talking about the viscoelastic properties of skin.
Oh.
And it seems to me that might be actually quite important to the computer class. Maybe. So
Okay.
if we have any ideas about
All right.
using software
I need to talk to him.
skin.
Okay. Matt mentioned Vincent Howard.
Vincent Hayward.
Vincent Hayward. He's at Canada, right?
He's at Paris.
Paris. Oh, he went to Paris?
Yeah.
Oh, okay. He has studied viscous elastic properties of the soft materials, okay, which might be very useful related to soft robots. Yeah. He's in Paris.
Thank you for Professor Wang. I have a question regarding the robotics. So if we want to get the strength and the precision, we want the robot to be as stiff as possible. But if we want the robot to interact with the environment and the human, we want the robot to be passively compliant. So what's your vision to how to balance these two ends? Well, many of the soft robots, as I see, is very weak. Basically, they are very, in practice, it's not have so many applications. So how to
I
towards the
philosophically, I don't think you can have both. You either utilize rigid body theory and electrical motor, you get your precision, speed, and payload. Once you get your physically compliant, you intrinsically would lose precision, and you would intrinsically lower your bandwidth, so your speed will be low, your payload will also be low. I do not see philosophically, I do not see the possibility to combine both. I just don't think you can possibly can have both ends of the world. You have to choose which way to go.
in the future, the robot will work with the humans, so the interaction and how to make it environment friendly very important. So the precision strength and also environment safe is the friendly is how to be get together.
So this idea of building passive compliance into the robot with hyperelastic material would give you the compliance you need, but you are going to lose precision. Even this type of actuators, the precision range is 1/10 millimeter at best, could be in the millimeter range, and you have not even considered the deformation. So the point I'm trying to make is that when you have a rigid body, when you have a motor, you drive your rigid body with the motor to a very good precision, and nothing will change that because that's the way you commanded to do. But when you have passive compliance into your system, and then your environment and your robot become an integral. It's one system. Okay? That's why in my equations, which I do not have time to explain, is that the behavior of the robot would also depend on the interaction. So much deformation, so much motion, not only comes from how much electricity, how much charge you put on your actuator, it also depends on the reaction forces. Okay. So you cannot absolutely control the precision because of the physical compliance. Right? Physical compliance. So if you, from a structural point of view, if you look at it from a mechanics point of view, the system are integrated now.
So is there any material until now that can change the compliance?
Actively,
Yes.
very few. Some of the so-called smart materials, chip memory alloy, some other types, but these are typically very hard materials. So you can change the stiffness, but still in that very large range, in the giga Pascal range. When you want to change from megapascal to gigapascal, that's almost impossible. Okay? So the hardware choices are very limited. So if you think about the robotics development, when we were undergraduate students, we had very limited hardware those days. Okay? Today, for soft robots, we are facing exactly same issue. The hardware technologies are not there, very limited, and fundamental theories are not there either. It's just getting started. So that's why I think this is still a good area because it's still wide open. A lot of issues are not being addressed. So for somebody like me, the very analytical person, I'm not very hands-on building things type. I'm more analytical, more looking at the basic equations. So this is a place where I think is good.
Thank you very much.
So you mentioned stiffness change. I wonder if you thought about things like electro-rheological materials, fluids.
You can use those as well. There are some actuators built out of those materials as well. They are not easily controllable. The variation range is fairly large, but certainly they are one of the choices. Yeah. So there are groups called smart materials. So they have been using some of these for different applications, but not to a level here this kind of a level of compliance. They are dealing with more or less variable impedance controls, right?
So many of these compliant mechanisms built with springy, stiff stuff are bistable or multi-stable.
Exactly.
You can have convex or concave, and they do what they want to do sometimes, not
Exactly.
what you want. Do you have the potential for similar problems with the elastic materials?
No, you could have the similar problem, but in general, you can alleviate those problems if you design it, if you distribute it. So one of the challenges in compliant mechanism area is that how do you get the deformation to be more uniformly spread out instead of just simply have had them to be one joint, one place. So for the morphing wing community, it's one of the major development issues. There are very good development today. Morphing wing structures now are quite practical. Smaller aircraft morphing wing is being demonstrated. NASA is still pumping money into it. They're still being believed to have real potentials. Yeah.
Well, it's, okay, the last question.
And do you think this has any size limitations because this is not kind of stiff? Do you think the robots have a limitation on size?
You cannot go too small if you stay with this type of a material. For example, micrometers, that's just not practical. In terms of the other end, you can go as big as human beings. That's probably not the issue, but of course, if it at that large size without rigid skeletons, and it will fall on its own gravity. So you would have difficulties. So I would think some size of bottle, this size, might be a good size for trying out, right? And when you get to real Michelin man, and you really need skeleton. That's why Nancy's model has skeletons inside. Otherwise, it's going to collapse on its own weight, right? Yeah. All right. Thank you all. Thank you all. Very rough, but it's okay. How come you lost your voice?